Welcome everyone to our session today on representation and demographics. I'm Stefan, an assistant professor at Northeastern University. I will be your chair today. The papers in this session are very interesting. They talk a lot about how you can overcome bias in your data samples, certain types of learning that you can find from biased samples. Also, what happens when you have limited demographic data. So let's take a deep dive into this fantastic session. We'll have good Q&A. Thank you everyone for joining us. And our first talk is with Roshni. She's from Stanford University, and she's going to be presenting on learning from a biased sample.
Hi everyone, my name is Roshni, and today I'll be presenting some work called Learning from a Biased Sample. So, this is joint work with my collaborators Lihua and Stefan. The motivation behind this work is that oftentimes when we're developing machine learning models, we want to train on data that comes from the same distribution as our target or deployment distribution. However, our sample selection procedure may be biased, meaning that certain groups may be over or underrepresented in our training data relative to our target distribution of interest. Before I get into how we solve this problem, we can think a little bit about what the data generating process looks like when we have sample selection. So to begin with, we can imagine that we have a target population Q. And for every individual in this target population, we have some observed covariates X and a label Y. And we can imagine that in order to collect people into our training population, there is a selection indicator S that is a binary random variable that's 0 or 1. And S can depend arbitrarily on X and it can depend arbitrarily on Y. And basically, our training population consists of the people in our target population that have S equal to 1. And our goal is, given some loss function L, we aim to learn a model H that is a mapping from the space of observed covariates X to the space of labeled Y that minimize our expected risk under the target population Q. The challenge, of course, is that when we're developing our model, we only have access to data from P, which isn't the target distribution that we actually care about. What people typically assume to get around this problem is something called ignorable selection. Under ignorable selection, we essentially assume that the selection probabilities only depend on observables. So basically, your selection indicator S doesn't depend on Y, or is conditionally independent from Y given X. If you're familiar with like the machine learning literature, this kind of assumption basically just assumes that you have only covariate shift, no conditional shift at all. In this work today, we'll be talking about what is possible under violations of ignorable selection, where your selection indicator S may depend on X and Y potentially. So to give a concrete example of ignorable versus non-ignorable selection, we can consider an online health survey that aims to measure vaccination status. We might imagine that younger people are more likely to opt in to participate than older people. That's an instance of ignorable selection because the people running the survey very likely can ask people what their age is and then reweight the survey responses to match the target distribution of interest. However, you can imagine that people who are more health conscious may be more likely to answer the survey. That's an instance of non-ignorable selection. And basically what happens here is your target outcome Y may influence how likely you are to answer the survey. So that conditional independence assumption doesn't hold anymore. The reason why this might be problematic in a concrete one-dimensional example is if our training distribution looks like something like the distribution on the left, and our test distribution looks like something on the right. What you'll notice is that in our test population, we have these two bands of outcomes that are in approximately equal proportion to each other. Whereas in our training distribution, we have undersample of units that have high outcomes and oversample of units with low outcomes. And now you can imagine if you go and try to fit a model on data from your training distribution, you would basically learn something that obtains low error on samples from the lower band, but high error on samples from the upper band. The ideal thing that you would have wanted to do is go and train a model based on data collected from your target distribution. That would have led to you learning H hat oracle, which is the model that lies between the two bands. So in our work today, we'll be trying to handle this problem of non-ignorable sample selection bias when you don't have access to data from your target distribution. So the idea of this work is that we want to learn a model from P that performs well under Q. And the problem is this isn't a really well defined task because we have no information on how our target distribution differs from our training distribution. So we need to make some assumptions. In this work, we proposed a particular model of sample selection bias called the gamma bias sampling model. In the gamma bias sampling model, we basically relaxed that ignorable selection assumption to allow the probability of sample selection to depend a bounded amount on the outcome y. So basically what we imagine is that we have some target distribution Q tilde, which is the distribution over x, y, and that selection indicator S. And the xy marginal of Q tilde is equal to Q, our true target distribution. And then conditioned on x equal to 1, we get our true training distribution. And for any x and y, we expect the probability of sample selection, that the true probability of sample selection, and that's computed just based on the covariates x, so lie in this bounded interval gamma inverse gamma. And what you can notice is that when gamma equals 1, this is equivalent to ignorable selection. And I often get this question, like, how would you know what gamma is if you're trying to use this model? For the purposes of this talk, gamma is a sensitivity parameter that is postulated by the analyst. I can talk a little bit later in the Q&A about how you might pick gamma through like a cross-validation procedure. So after you make this assumption of gamma bias sampling, you can basically form an uncertainty set for Q. And how this uncertainty set works is basically we say that the set of distributions S gamma PQX is the set of possible target distributions that could arise given our training data P and our assumption on the amount of bias sampling. And so when I say that I want to learn a model from P that performs well under Q, what I actually mean is I want to learn a model from P that performs well over the robustness set S gamma P. Okay. And that leads to a distributionally robust optimization problem, where we basically are trying to learn a model H that performs well over the uncertainty set S gamma PQX. And in order to perform well over this set, what we can do is we can try to find the distribution that's the hardest in this set and make sure our model performs well on that hardest instance. The challenge here, of course, is that the min-max formulation of this problem isn't amenable to standard statistical learning. Typically in statistical learning, we're just focused on loss minimization. But the main contribution of our work is that we're able to convert that challenging min-max problem into a very tractable min-min problem, where, and we call this min-min problem Rockafellar and Uryasev regression because it derives on a classical result of Rockafellar and Uryasev. And we basically are able to show that that min-max problem can be written as a very simple convex loss minimization problem. And I won't get into too much of the detail on how we derive this, but the key insight here is that we're able to show that our worst case risk depends on some quantity called the conditional value at risk for the C bar. And the C bar itself can be written as, what the C bar is basically the expectation of a random variable conditioned on it being greater than a particular quantile of its distribution. And so a key result of Rockafellar and Uryasev is that the C bar itself can be expressed as the solution to a minimization problem. So we can basically plug in that minimization problem into our worst case risk. And that massaging this a little bit further gives us Rockafellar-Uryasev regression, or our desired loss minimization problem. And this is a very straightforward implementation. We can use two neural networks and basically jointly train them to minimize the RU loss. And then we can find that, like, for different parameter settings of gamma, we can learn what the robust regression function would look like in this case. And we see that as we increase gamma, well, so when gamma is equal to 1, we actually learn our method is equivalent to just running standard risk loss minimization over P. And then as we increase gamma, we are asking to be robust to a higher and higher level of non-ignorable selection bias. So in this particular case, we are able to learn a model that performs better on the target distribution of interest. This won't always be the case. There will typically be a gap between the oracle model and the target distribution and the robust model. But we can see that we can get some robust guarantees in this case. So thanks so much for listening. That's all.
Let's open it up now for questions. Oh, we have a question in the back.
Yeah, I can talk. Can you tell a little bit about, I think that there's like a variance right up here. When you increase gamma, you might cover some less bias distribution, but then it's working with the space of distribution. So what can you balance that and that can convert that estimator when where you get like white gamma?
Yeah, so your intuition is exactly right that, like, as you increase gamma, you're asking to be robust to a larger and larger family of distributions. So like as you increase gamma, maybe if you increase it too far, then you'll end up with something that's more conservative than you want to be, because you're trying to be robust to distributions that you don't necessarily need to be robust to. So yeah, that is a concern with any type of robust optimization type approach. And that's why when you're working on more applied settings, like thinking carefully about like how you might pick gamma, if you have some access to ground truth information, such as like even aggregate statistics, like even if you don't have access to Q, if you have access to aggregate statistics, I found that in like when I've worked on applied projects that like if I have access to aggregate statistics of Q, I can use that to help pick gamma better through like a cross validation approach.
Excellent. Do we have other questions? And anybody else, or I can maybe share one. I don't know if you can provide a little bit of intuition about how distributively robust optimization aids in tackling the challenges posed by sampling bias and decision-making processes.
Oh, that's a great question. So I actually have another work on that topic exactly, which is like, say you're trying to make a binary decision based on data collected from a biased sample. I have another paper that focuses, it's called policy learning under biased sample selection, and it basically uses related ideas here, but extends it to the setting where you're making basically like binary treatment allocation decision based on that. So a lot of these ideas transfer, but it is it is more challenging the decision making setting, because basically you have to deal with counterfactual outcomes then. What happens if you gave someone the treatment or didn't? That also affects like how you should formulate your robust optimization problem.
Excellent, excellent, thank you. Let's give this author a round of applause.